A star floating in Libra defies the laws of physics. When astronomers first calculated its age, they got a number that made no sense: 14.5 billion years old. The problem? Our entire universe is only 13.8 billion years old. This star appeared to be billion years older than existence itself. If the measurements were correct, everything we knew about reality was wrong. But what actually happened is even stranger. In the year 2000, a team of astronomers made a calculation that should have been routine. They were measuring the age of HD 140283, a star that had caught their attention decades earlier. They ran the numbers through their models. They checked their data. Then they checked again. The result made no sense whatsoever. The star was 16 billion years old. Here's why that number caused panic. Our universe, according to decades of careful measurement, is 13.8 billion years old. Everything that exists, every galaxy, every planet, every atom, came into being at that moment. Nothing can be older than the universe itself. That would be like finding a tree that grew before dirt existed. But the math was clear. This star, sitting just 190 light-years away in the constellation Libra, appeared to have been born 2 billion years before the Big Bang even happened. Scientists had three possibilities to consider. First, maybe their measurements of the star were completely wrong. Second, maybe our understanding of how stars age was fundamentally broken. Or third, maybe the entire scientific community had miscalculated the age of the universe itself. Every option was terrifying. The discovery went public almost immediately. Headlines screamed about the star that broke physics. Television networks brought on experts to explain how this could shatter our understanding of reality. Online forums exploded with theories ranging from reasonable to absolutely wild. Some people saw it as proof that the Big Bang never happened. Others wondered if we lived in a simulation with a programming error. What made this particularly troubling was the method used to date the star. It wasn't some experimental technique that could easily be dismissed. Astronomers had used the same proven approaches they relied on for countless other stellar measurements. The data came from respected observatories. The calculations followed standard models that had worked perfectly well for decades. The star itself looked completely normal in most ways. It wasn't some bizarre object at the edge of known physics. HD 140283 followed the rules of stellar evolution. It burned its fuel predictably. Its luminosity matched expectations. Its mass fell within normal ranges. Everything about it made sense except for one impossible detail: its age. Scientists around the world began scrambling to figure out what went wrong. Research teams requested telescope time to gather new observations. Theorists started reviewing the fundamental equations used to calculate stellar ages. Cosmologists wondered if they needed to revise the entire timeline of universal history. The pressure was enormous. This wasn't just an interesting puzzle. It was a potential crisis that could unravel a century of carefully constructed knowledge. But before anyone could solve the mystery, they needed to understand something else. They needed to know why this particular star revealed its impossible age in the first place. And that story begins billions of years earlier, in a universe that looked nothing like the one we see today. The star hides in plain sight. If you know where to look, you can find HD 140,283 inches, the constellation Libra. It sits just 190 light-years away. In cosmic terms, that makes it a close neighbor. Most of the stars you see at night are hundreds or thousands of times farther away. This ancient object is practically in our backyard, but you cannot see it without help. The star has an apparent magnitude of 7, which puts it just below the threshold of human vision. On a perfectly clear night, far from city lights, your eyes can detect objects down to magnitude 6. This star falls just short. Hand someone a decent pair of binoculars, though, and it suddenly becomes visible. A small telescope makes it easy. Astronomers first catalogued it in the early 20th century as part of massive sky surveys. Back then, They had no idea it was special. It was just another dim point of light, one among millions being documented and numbered. HD 140283 got its name from the Henry Draper Catalogue, an ambitious project that classified hundreds of thousands of stars based on their spectral properties. For decades, it remained anonymous. No one paid particular attention to it. No one suspected it held any secrets. That changed in 1951. An astronomer named Joseph Chamberlain was studying stellar composition using a technique called spectroscopy. When light from a star passes through a prism, it splits into a rainbow of colors. But that rainbow isn't smooth. It contains dark lines, gaps where specific wavelengths are missing. Each chemical element absorbs light at unique wavelengths, creating a distinctive pattern. By reading these patterns, scientists can determine exactly what a star is made of. Chamberlain pointed his instruments at HD 140283 and saw something unexpected. The spectral lines revealed extremely low levels of heavy elements. Iron, one of the most common metals in younger stars, appeared in tiny amounts. Compared to our own stellar neighborhood, this star contained less than 0.5% of the iron astronomers normally expected. This was the first major clue. Heavy elements like iron are not created during the Big Bang. They form inside stars through nuclear fusion, then spread through space when those stars explode. A star with very little iron must have formed early, before many generations of stars had lived and died and scattered their enriched material through the cosmos. But just how early? That question would take another 50 years to answer properly. For most of the late 20th century, HD 140283 was simply known as an old metal poor star. Scientists understood it came from an ancient population. They knew it witnessed the early days of our galaxy, but they had no precise age. The technology and methods needed to calculate that number accurately did not exist yet. When those methods finally arrived at the turn of the millennium, the answer they provided shocked everyone, and suddenly, this quiet neighbor became the most controversial object in astronomy. 16 billion years sounds like just a number until you understand what it means. Imagine finding a photograph dated 20 years before cameras were invented. That's essentially what astronomers discovered with HD 140283. The star's calculated age didn't just push boundaries, it shattered them completely. The measurements came from careful analysis using multiple data points. Astronomers examined the star's brightness, its temperature, its chemical composition, and its distance from Earth. They plugged all this information into stellar evolution models, sophisticated computer simulations that predict how stars change over time. These models had been tested and refined for decades. They worked extremely well for thousands of other stars. When applied to HD 140283, the models produced a clear result. 16 billion years, give or take a few hundred million. The universe, according to our best measurements, began 13.8 billion years ago. That number comes from multiple independent sources that all agree remarkably well. The difference between these two numbers was 2.2 billion years. That's not a small margin of error. That's not a rounding issue. That's a gap large enough to fit the entire history of complex life on Earth multiple times over. Scientists immediately recognized the implications. If the star really was that old, one of three things had to be true. Either our measurements of the star were wrong, our models of stellar evolution were wrong, or our understanding of the universe's age was wrong. Any option represented a fundamental breakdown in modern astrophysics. The timing made everything worse. The early 2000s marked a period when cosmology seemed to be settling into comfortable certainty. The Big Bang theory had won over nearly all skeptics. Satellite measurements had pinned down the universe's age with impressive precision. Dark energy had just been discovered, filling in the last major piece of the cosmological puzzle. Everything seemed to fit together beautifully. Then this star showed up and kicked over the entire table. Skeptics of the Big Bang immediately seized on the finding. Here was quantifiable evidence, they argued, that mainstream cosmology had made critical errors. Online discussions became heated. Some scientists received angry emails accusing them of covering up evidence. Others faced questions from administrators wondering if decades of research funding had been wasted. But most astronomers didn't panic. They recognized that extraordinary claims require extraordinary evidence, and a single measurement, however careful, could have hidden problems. The smart money said someone had made a mistake somewhere. The question was where. Still, the unease was real. Even scientists confident the issue would be resolved felt a small knot of worry. What if the measurements held up? What if repeated studies confirmed the 16 billion year age? That would force a complete re-evaluation of everything cosmology had accomplished over the past century. The star wasn't going anywhere. It would keep shining in Libra, patiently waiting while humans tried to figure out whether it was older than existence itself, or whether their instruments and theories had failed them. And before anyone could solve that mystery, they needed to understand something more fundamental. They needed to understand what stellar ages actually tell us about the universe. Every star is a time capsule. When you measure a star's age, you're not just satisfying curiosity. You're reading a historical record written in light and atoms. Each star preserves information about the conditions that existed when it formed. The chemical elements it contains tell you what materials were available billions of years ago. Its mass and brightness reveal what kind of clouds collapsed to create it. Everything about a star encodes data about a specific moment in cosmic history. This matters because we cannot observe the past directly. Light takes time to travel, so looking at distant galaxies shows us how they appeared millions or billions of years ago. But that technique has limits. We can only see bright objects. Faint stars and small planets remain invisible across large distances. Direct age measurements let us fill in gaps that observation alone cannot reach. Knowing when stars formed also helps us understand how galaxies evolve. Our own Milky Way didn't appear all at once. It built up gradually over billions of years as gas clouds collapsed, stars ignited, and smaller galaxies merged together. By measuring the ages of stars in different regions, astronomers can reconstruct that history. They can figure out which parts formed first and which came later. HD 140283 represented something even more valuable. Its low metal content suggested it formed very early, during an era when few heavy elements existed. If scientists could pin down its exact age, they would have a direct measurement of when stars first began forming after the Big Bang. That single data point could confirm or challenge theories about the early universe. But dating stars is incredibly difficult. Unlike trees, they don't grow rings you can count. Unlike rocks, they don't accumulate radioactive decay products you can measure. All you have is the light they emit right now. From that light, you must work backward through billions of years of complex physics to figure out when they were born. The process relies on stellar evolution models. These computer simulations track how stars change over time as they burn through their fuel. A star's current brightness, temperature, and size depend on how much fuel it has left, which depends on how long it has been burning. By matching a star's observed properties to the models, astronomers can estimate its age. The problem is that those models require accurate input data. If you miscalculate the star's distance, you'll miscalculate its true brightness. If you misjudge its chemical composition, you'll miscalculate how efficiently it burns fuel. Small errors in measurement propagate through the calculations and can produce wildly wrong ages. This is why the Methuselah star caused such controversy. The age calculation depended on a long chain of assumptions and measurements. Any link in that chain could potentially be wrong. But which one? And even if scientists found the error, would fixing it be enough to bring the star's age below the universe's age? Those questions needed answers fast. The longer the mystery remained unsolved, the more people would question whether our fundamental understanding of the cosmos was completely broken. But to understand what went wrong, you first need to understand what the early universe was actually like. The universe started simple. In the first moments after the Big Bang, reality consisted of an impossibly hot soup of elementary particles. Protons, neutrons, and electrons flew around in a chaotic dance, moving too fast and colliding too violently to stick together. Nothing solid could form. Nothing stable could exist. Just pure energy gradually cooling as space itself expanded. This phase didn't last long. After about 380,000 years, temperatures had dropped enough for the first atoms to assemble. Protons captured electrons, creating the simplest element in existence: hydrogen. One proton, one electron, nothing more. Some protons had fused together earlier, during the first few minutes, when temperatures were still extreme enough for nuclear reactions. These paired protons captured neutrons and formed helium nuclei. When the universe cooled and electrons got captured, these became helium atoms. 2 protons, 2 neutrons, 2 electrons. And that was everything. No carbon, no oxygen, no iron, silicon, or gold. No elements that make up rocks, water, or living things. Just hydrogen and helium in a ratio of roughly 3:1. The entire universe contained only the 2 simplest atoms possible. This might sound limiting, but these 2 elements were enough. Gravity began pulling hydrogen and helium together into dense clouds. These clouds continued collapsing under their own weight. As they compressed, their cores heated up. Temperatures rose. Pressure increased. Eventually, conditions became extreme enough for nuclear fusion to ignite. The first stars were born. Scientists call this population 3, and we've never actually seen one. They existed too long ago, too far away, at a time when the universe was young and small. Every population 3 star that ever formed has long since died, but we can infer what they must have been like based on physics. They were monsters. Without heavy elements to help radiate heat away, these stars had to be massive just to maintain stable fusion. Current models suggest they ranged from 60 to 300 times more massive than our local stellar neighbor. They burned incredibly hot, shining with the light of millions of present-day stars combined. You might think bigger means longer lasting. It doesn't. Massive stars burn through their fuel at catastrophic rates. The stronger gravity squeezes their cores, the hotter the fusion reactions run, and the faster they consume their hydrogen supply. A star 300 times more massive might last only a few million years. Compare that to smaller stars that can keep burning for trillions of years. Population 3 stars lived fast and died violently. When their fuel ran out, their cores collapsed catastrophically. The outer layers rebounded in tremendous explosions. Supernovae, the biggest explosions that single stars can produce. These detonations did something crucial. They created new elements. During the brief moments of collapse and explosion, temperatures and pressures reached levels where nuclear fusion could create heavier atoms. Carbon, oxygen, silicon, iron. Elements that never existed before suddenly flooded into space. When the next generation of stars formed from those enriched gas clouds, they inherited this chemical legacy. That next generation included stars like HD 140283, and the amount of heavy elements they contained would become the key to understanding their age. Nobody has ever seen a population 3 star. That statement might sound strange given how much scientists talk about them, but it's absolutely true. These objects remain entirely theoretical, predicted by physics but never directly observed. We know they must have existed because the universe couldn't have evolved without them, but finding actual evidence of one has proven impossible so far. The problem is distance. Population 3 stars formed during the first few 100 million years after the Big Bang. Light from that era has been traveling toward us for over 13 billion years. By the time it reaches our telescopes, it's incredibly faint. Current instruments can barely detect entire galaxies from that period, let alone individual stars. Even if we could see that far clearly, we probably wouldn't find any population 3 stars still burning. These giants had extraordinarily short lifespans. Most would have exhausted their fuel and exploded within 10 million years of forming. The last population 3 star likely died over 12 billion years ago. We're not looking for living stars. We're looking for ancient ghosts, but scientists haven't given up. The James Webb Space Telescope, launched in 2021, has the sensitivity to potentially spot evidence of these early giants. It might not image them directly, but it could detect their distinctive light signatures in the spectra of very distant galaxies. A few research teams have claimed possible detections, though none have been confirmed yet. Why does finding them matter? Because Population 3 stars did something that changed everything. They created the first heavy elements through nuclear fusion in their cores. Without that process, the universe would still be just hydrogen and helium. No rocky planets would exist, no complex chemistry, no life. The fusion process works like this. Inside a star's core, intense heat and pressure force hydrogen nuclei to slam together and merge. This creates helium and releases energy. As the star ages and its core gets hotter, helium nuclei start fusing into carbon. Carbon fuses into oxygen. The process continues, building heavier and heavier elements. For the most massive Population 3 stars, this chain reaction continued all the way up to iron. They had cores hot enough to fuse silicon into iron atoms, but iron represents a wall. Fusing iron requires energy instead of releasing it. Once a massive star's core fills with iron, fusion stops completely. Without fusion pushing outward to balance gravity pulling inward, the core collapses in less than a second. The collapse rebounds in a catastrophic supernova explosion. In that brief moment of destruction, even heavier elements form through rapid neutron capture. Gold, uranium, and all the elements heavier than iron get created during these violent deaths. The debris from these explosions spread through space, mixing with surrounding hydrogen and helium. When the next generation of stars formed, they incorporated these new elements into their structure. Those second-generation stars became known as Population 2, and they had a crucial difference from their predecessors. They contained metals, not much, but enough to measure. HD 140283 is a Population 2 star. Its tiny amount of iron proves it formed after at least one previous generation had lived and died. But the amount is so small that it must have formed very early, when only a few Population 3 stars had exploded, which raises the question scientists desperately needed answered. Exactly how early the biggest stars have the shortest lives? This seems backward at first. You'd think more fuel means longer burning time. A cargo ship with a larger tank should travel farther than one with a small tank. But stars don't follow that logic. The relationship between mass and lifespan moves in the opposite direction. Double a star's mass, and you cut its lifetime by about 90%. Gravity explains everything. Imagine two balls of gas floating in space. One has 10 times the mass of the other. The larger ball creates stronger gravitational forces, pulling all its material inward. That stronger pull squeezes the core much more tightly. Tighter squeezing means higher pressure. Higher pressure means higher temperature. And higher temperature makes nuclear fusion run dramatically faster. Our local stellar neighbor will burn steadily for about 10 billion years. It's currently middle-aged at around 4.6 billion years old. A star with 10 times that mass might last only 20 million years. A star with 100 times that mass could exhaust its fuel in barely 2 million years. The difference is staggering. Population 3 stars likely fell into this ultramassive category. Without heavy elements in their composition, they couldn't cool efficiently. Their gas clouds had to collapse into very large objects just to achieve the densities needed for stable fusion. Once ignited, these monsters burned with terrifying intensity. Their cores reached temperatures exceeding 100 million degrees. At those extremes, hydrogen fused into helium at incredible rates. The energy output was mind-boggling. A single Population 3 star probably shone brighter than an entire modern galaxy containing billions of smaller stars. But all that power came at a cost. These giants consumed their hydrogen supplies in cosmically short timescales. Within a few million years, their cores had converted most of their hydrogen into helium. Then, the helium started fusing into carbon and oxygen. Those heavier elements fused into neon, then magnesium, then silicon. Each stage burned faster than the last because the star's core kept getting hotter as it contracted. Finally, silicon fused into iron, and there the process stopped. Iron fusion doesn't release energy, it absorbs energy. You cannot power a star by fusing iron. Once the core filled with iron atoms, the star's energy production shut down completely. In less than a second, gravity won. The core collapsed catastrophically, compressing to a fraction of its original size. Temperatures spiked into the billions of degrees. The outer layers came crashing inward, then rebounded off the collapsing core. The rebound launched a shockwave traveling outward at thousands of miles per second. As it passed through the star's layers, it ripped them apart. The star exploded, a supernova. For a few weeks, that single exploding star outshone its entire host galaxy. The explosion released more energy in 1 month than our local stellar neighbor will emit in its entire 10 billion year lifespan. The debris scattered into surrounding space at thousands of miles per second, carrying the newly formed heavy elements with it. These cosmic catastrophes seeded the universe with the ingredients for future worlds. Every iron atom in your blood, every calcium atom in your bones, every gold atom in jewelry, came from the violent death of an ancient massive star. You are literally made of stardust, scattered by these explosions. An HD 140283 formed in that enriched material. But how much enrichment had occurred by the time it ignited? Iron reveals secrets written billions of years ago. When astronomers point spectrographs at distant stars, they're not just measuring brightness, they're reading chemical fingerprints. Every element absorbs light at specific wavelengths, creating dark lines in the spectrum. The pattern of these lines acts like a barcode, identifying exactly which elements exist in the star's outer layers and how much of each. For HD 140283, the iron signature was shockingly weak. Our local stellar neighbor's spectrum shows strong iron absorption lines. The star contains iron throughout its outer layers because it formed from gas clouds enriched by many generations of stellar deaths. HD 140283's spectrum barely shows iron at all. When scientists measured the abundance carefully, they found this ancient star contains only 0.4% as much iron as our stellar neighborhood. That tiny fraction tells a profound story. It means HD 140283 formed when very few supernovae had occurred. The gas cloud that collapsed to create this star came from an era when the universe was still almost entirely hydrogen and helium. Only a handful of massive population 3 stars had lived, died, and scattered their enriched material into space. But iron isn't the only element scientists measured. They also looked for other heavy elements like calcium, magnesium, and titanium. All showed similar depletion. The overall metallicity, a term astronomers use for all elements heavier than helium, was extremely low. This confirmed that HD 140283 belonged to the population 2 category, the second generation of stars to form after the Big Bang. The detection came from spectroscopy, a technique developed in the 1800s. Back then, scientists had no idea what those dark lines in stellar spectra meant. They just noticed that different stars showed different patterns. Eventually, they realized the patterns matched the absorption lines of specific elements heated in laboratory flames. Modern spectrographs are far more sophisticated than those early instruments. They can detect elements present in concentrations of parts per billion. They can measure dozens of different elements simultaneously, and they can do it for stars hundreds of light years away. When Joseph Chamberlain first examined HD 140,283 inches, 1951, he was using relatively primitive equipment compared to today's standards. But even his basic measurements revealed the star's unusually low metallicity. That observation made it scientifically interesting. It suggested the star had formed early in galactic history. But Chamberlain couldn't calculate a precise age. The technology didn't exist yet. The stellar evolution models weren't advanced enough. The distance measurements weren't accurate enough. He could only note that this star appeared to be very old and should be studied more carefully in the future. That future arrived 50 years later when improved instruments and refined models finally made accurate age calculations possible. And when scientists ran those calculations, they got the impossible 16 billion year result that launched the whole controversy. The low iron content was both the evidence and the problem. It proved the star was genuinely ancient. But it also made age calculations more difficult, because metal-poor stars evolve slightly differently than metal-rich ones. The models had to account for that difference. Any errors in how they handled low metallicity stars could throw off the final age estimate significantly. So scientists had good reason to believe HD 140283 was old. The question was whether it was impossibly old or just extremely old. That distinction would determine whether our understanding of the universe was broken or merely imperfect. HD 140283 belongs to the second generation. Population 2 stars formed after the first wave of stellar deaths, but before the universe became thoroughly enriched with heavy elements. They represent a middle chapter in cosmic history, more evolved than the purely primordial population 3, but still fundamentally different from modern population 1 stars like our stellar neighbor. The classification system confuses everyone at first because it runs backward. You'd expect population 1 to be the oldest, but astronomers named them in the order of discovery, not formation. They identified population 1 stars first because those are the most common and easiest to study. Population 2 stars came later. Population 3 remains theoretical. What defines each population is metallicity. Population 1 stars like our stellar neighbor contain roughly 2% heavy elements by mass. That might sound small, but it's huge compared to population 2. HD 140283 contains less than 0.01% heavy elements. Population 3 stars would contain essentially zero. These tiny differences have enormous consequences. Heavy elements help stars radiate heat more efficiently. They provide more pathways for energy to escape from the stellar interior. A metal-rich star can maintain the same temperature and pressure with less mass than a metal-poor star needs. This affects everything from how stars form to how they age. Population 2 stars tend to be hotter and more luminous than population 1 stars of the same mass. They also evolve differently. Their cores burn slightly faster because they lack the cooling efficiency that metals provide. This means they progress through their life stages more quickly, though the differences are subtle and require careful modeling to detect. HD 140283 currently exists as a subgiant. This phase comes after the main sequence, when a star has exhausted the hydrogen in its core and begins fusing hydrogen in a shell around the core. The star expands and becomes more luminous. Our stellar neighbor will enter this phase in about 5 billion years. HD 140283 entered it billions of years ago. The subgiant phase is relatively brief, lasting only about 1 billion years for a star of HD 140283's mass. After that, it will continue expanding into a red giant, becoming hundreds of times larger than it is now. Eventually, it will shed its outer layers, leaving behind a white dwarf that will glow dimly for trillions of years. But right now, HD 140283 is still actively fusing hydrogen into helium. It's still generating energy through nuclear reactions. It's still very much alive, just old. The same way a 70-year-old human is old but not yet approaching the end of their natural lifespan, scientists can tell HD 140283 is a subgiant by examining its spectrum carefully. The spectral lines have subtle characteristics that reveal the star's surface gravity and temperature. These parameters, combined with its luminosity, place it precisely in the subgiant phase of stellar evolution. This classification helped narrow down the age calculations. Scientists knew roughly how long stars spend in each evolutionary phase. By identifying which phase HD 140283 occupied, they could work backward to estimate when it first ignited. The math was complex, but it relied on well-tested principles. or so they thought, because when they finally ran all the numbers, the result defied everything they believed about the universe. And it all started with measurements from a satellite orbiting Earth. A European spacecraft revealed the impossible. In 1989, the European Space Agency launched Hipparcos, a satellite designed to measure stellar positions and distances with unprecedented precision. The name stood for High Precision Parallax Collecting Satellite, though it also paid homage to the ancient Greek astronomer Hipparchus, who created the first comprehensive star catalogue over 2,000 years earlier. Hipparcos orbited Earth for 4 years, scanning the sky methodically. It measured over 118,000 stars, recording their positions accurate to less than 1,000th of an arcsecond. That's like measuring the width of a human hair from 10 miles away. The precision was revolutionary. One of those stars was HD 140283. Distance measurements matter enormously for age calculations. If you know how far away a star is, you can calculate its true brightness from its apparent brightness. True brightness depends on the star's size and temperature, which depend on how much fuel it has burned, which depends on its age. Get the distance wrong, and every calculation downstream becomes wrong too. Before Hipparcos, distance measurements for stars like HD 140283 carried significant uncertainty. Astronomers had rough estimates, but not precise values. Hipparcos changed that by using parallax, the apparent shift in a star's position as Earth orbits around the stellar neighbor. Hold your finger in front of your face and close one eye, then the other. Your finger appears to jump back and forth against the background. That's parallax. The same thing happens with stars. As Earth moves through its orbit, nearby stars appear to shift slightly against more distant background stars. The amount of shift reveals how far away they are. Hipparcos measured these tiny shifts with extraordinary accuracy. For HD 140283, it determined a distance of approximately 190 light-years. That was close enough for detailed study, but far enough that light had been traveling since the early 1830s to reach us. With this precise distance, astronomers could calculate the star's true luminosity. Combined with its temperature and chemical composition, they had all the ingredients needed for an age calculation. They fed the numbers into stellar evolution models, sophisticated computer programs that simulate how stars change over billions of years. The models ran, the calculations completed, and the result was 16 billion years. The Hipparcos team published their findings in the early 2000s. The scientific community immediately recognized the problem. The age exceeded the universe's age by 2 billion years. Something was seriously wrong. Either the satellite measurements contained an error, the stellar models had fundamental flaws, or cosmologists had miscalculated the age of everything. The controversy exploded across academic journals and conferences. Papers appeared arguing different positions. Some scientists suggested the distance measurement might be slightly off. Others wondered if metal-poor stars evolved differently than the models predicted. A few radical voices questioned whether the Big Bang timeline needed revision. But most astronomers remained confident the issue would resolve. Extraordinary claims require extraordinary evidence, and a single measurement, however precise, isn't enough to overturn decades of confirmed cosmology. The smart bet was that someone would find the error and the age would drop to something reasonable. Nobody expected it would take over a decade to sort out, and nobody expected the solution would reveal just how difficult measuring stellar ages really is. What seemed like a simple mistake turned into a profound lesson about the limits of our knowledge. The impossible star gave ammunition to skeptics everywhere. For decades, fringe scientists and alternative theorists had questioned whether the Big Bang really happened. They pointed to supposed inconsistencies, unexplained observations, and alleged cover-ups. Mainstream astronomy dismissed most of these arguments because they relied on misunderstandings or outdated data. But HD 140283 was different. This was solid evidence produced by respected researchers using standard methods. Suddenly, The critics had something concrete to point at. Online forums exploded with discussion. Articles appeared in alternative science publications. Even a few credentialed scientists who had always been skeptical of the Big Bang began writing papers suggesting this star proved the theory needed fundamental revision or complete replacement. The timing couldn't have been worse for mainstream cosmology. The late 1990s and early 2000s had seemed like a golden age. Satellite measurements had pinned down the universe's age to within 1%. The cosmic microwave background matched theoretical predictions perfectly. Dark energy had been discovered, explaining why the universe's expansion was accelerating. Everything fit together beautifully. Then this ancient star showed up and created chaos. The media loved the story. Headlines screamed about scientists being wrong about the universe's age. Television documentaries featured dramatic recreations of astronomers staring in shock at their data. Popular science writers penned articles wondering if we needed to tear up the textbooks. The public, already suspicious of experts changing their minds, saw this as evidence that scientists didn't really know what they were talking about. Some of the criticism was fair. Science progresses by questioning established ideas and following evidence wherever it leads. If measurements consistently showed the universe was older than currently believed, scientists should consider that possibility seriously. Rejecting new evidence just to preserve existing theories would be the opposite of good science. But most astronomers weren't rejecting the evidence. They were trying to understand it. Big difference. The star's measured age came from a complex chain of observations and calculations. Any link in that chain could contain errors. Before abandoning a theory supported by mountains of other evidence, you need to rule out simpler explanations like measurement, mistakes, or modeling problems. The controversy did force one important conversation, though. It made scientists confront how certain they really were about the universe's age. That 13.8 billion year figure came from multiple independent methods that all agreed remarkably well. But independent doesn't mean infallible. If some hidden systematic error affected all the methods similarly, they could all be wrong in the same direction. Cosmologists went back through their calculations with fresh eyes. They re-examined the assumptions built into their models. They looked for potential sources of error that might have been overlooked. The scrutiny was good for science, even if the motivation came from unwanted controversy. Meanwhile, other astronomers focused on the star itself. If they could find problems with its age calculation, the whole controversy would disappear. The universe's age would remain secure. The skeptics would lose their best argument, and cosmology could return to business as usual. But that required understanding where the 16 billion year number came from. Why did this particular star seem so impossibly ancient? The answer lay in mythology, ancient scripture, and a name that perfectly captured the bewildering nature of this cosmic mystery. The press needed a better name than HD 140283. Journalists writing about the impossibly old star faced a problem. Scientific designations like HD 140283 or Hipparcos catalog numbers don't grab readers' attention. They're accurate but boring. News articles need hooks, memorable phrases that stick in people's minds and encourage sharing. Someone, probably a science writer looking for a catchy headline, remembered the biblical character Methuselah. According to the book of Genesis, Methuselah was the grandfather of Noah and the longest-lived person in Scripture. He supposedly reached the age of 969 years before dying, just before the Great Flood. Whether that's literal history or metaphorical storytelling remains debated among religious scholars. But the name had entered common language as a shorthand for extreme age. Calling something Methuselah meant it was ancient, weathered, incredibly old, perfect for a star that appeared older than the universe itself. The nickname caught on immediately. Within weeks of the age calculation becoming public, news articles and scientific papers were referring to HD 140283 as the Methuselah star. The name appeared in headlines worldwide. It showed up in conference presentations. Even skeptical scientists who disagreed about the implications used the nickname because it was simply more memorable than the catalog number. This kind of informal naming happens fairly often in astronomy. Scientists discover or identify something interesting, and if the official designation is boring, someone coins a catchier alternative. The pillars of creation, the hand of God, the eye of Sauron. These aren't official astronomical names, but they're what everyone actually uses. The Methuselah star joined that tradition, though in this case, the nickname carried extra weight. It wasn't just highlighting the star's age, it was emphasizing the biblical impossibility. Just as Methuselah lived longer than any human reasonably should, this star had apparently existed longer than physics allowed. Some religious groups saw the name choice as inappropriate. They felt it trivialized scripture by comparing sacred text to a cosmological puzzle. Others embraced it, arguing that the star's existence proved ancient texts contained hidden scientific truths that modern astronomy was only beginning to understand. Both reactions missed the point. The nickname was just a convenient label, not a theological statement, but the name did serve one useful purpose. It kept the story in public consciousness. Years after the initial discovery, people still recognized the Methuselah star reference. Journalists could mention it without lengthy explanations. Educators could use it to introduce discussions about stellar ages and cosmic timelines. The name had sticking power. Behind the scenes, astronomers were working furiously to resolve the age paradox. The nickname might have been fun, but the underlying problem was serious. If they couldn't figure out what went wrong, it would undermine confidence in cosmology as a whole. Too much was riding on this to let it remain a mystery. The solution required going back to basics. They needed to understand how scientists measure the universe's age in the first place. Only then could they figure out whether the measurements were solid or whether hidden errors might have thrown everything off. The first step was examining the cosmic microwave background, the oldest light in existence. The universe left behind a baby picture. About 380,000 years after the Big Bang, something remarkable happened. The universe had been expanding and cooling since its explosive beginning. Finally, temperatures dropped below 3,000 degrees. At that point, electrons and protons could stick together to form stable hydrogen atoms. Before this moment, light couldn't travel far. Free electrons scattered photons constantly, making the universe opaque like thick fog. But once atoms formed, photons could suddenly fly freely through space. The universe became transparent. Light escaped and began traveling outward in all directions. That ancient light is still traveling today. We call it the cosmic microwave background radiation. Every cubic inch of space contains photons that have been journeying through the universe for over 13 billion years. They've been stretched by cosmic expansion from visible light into microwaves, but they're still here, still detectable. Scientists first discovered this radiation accidentally in 1964. Two researchers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate annoying static from a radio antenna. They couldn't get rid of it. The noise came from every direction equally. Eventually, they realized they'd found the afterglow of the Big Bang itself. Modern satellites measure this radiation with incredible precision. The most recent mission, the Planck spacecraft, mapped tiny temperature variations across the entire sky. These variations are minuscule, just a few millionths of a degree, but they reveal crucial information about the early universe. Here's why this matters for calculating age. The pattern of temperature variations depends on specific physical conditions that existed when the light was released. Things like the density of matter, the expansion rate, and the ratio of different types of energy. By measuring the pattern carefully, scientists can determine those initial conditions. Once you know the initial conditions, physics takes over. The equations governing cosmic expansion are well understood. You can run them forward to predict how the universe evolved, or run them backward to calculate when everything began. It's like watching a video in reverse. If you know the current frame and the playback speed, you can figure out when the video started. The Planck satellite data produced a remarkably precise answer. 13.797 billion years, plus or minus about 20 million years. That uncertainty represents less than 0.2%. It's an extraordinarily confident measurement. But here's the key point. This age determination doesn't depend on measuring individual stars or galaxies. It comes entirely from the cosmic microwave background radiation, the oldest light we can observe. The calculation relies on different physics, different observations, and different assumptions than stellar age measurements. That independence is crucial. If only one method existed to measure the universe's age, we'd have reason to worry that some hidden error was affecting the result. But multiple methods, reaching similar conclusions, provide strong confirmation. It's like three witnesses giving matching testimony, much more credible than one witness alone. Still, scientists wanted another independent check. They wanted a completely different approach to measuring cosmic age that didn't rely on the microwave background at all. Fortunately, such a method exists. It comes from watching how fast the universe is expanding right now and calculating backward to figure out when the expansion began. The universe is expanding, and we can measure exactly how fast. In the 1920s, astronomer Edwin Hubble made a discovery that revolutionized cosmology. He found that distant galaxies are moving away from us. More surprisingly, the farther away a galaxy is, the faster it's receding. This relationship, now called Hubble's law, provides a completely independent way to calculate the universe's age. The logic is straightforward. If galaxies are moving apart, they must have been closer together in the past. Run the expansion backward, and eventually, everything converges to a single point. The time it takes to reach that point, running the clock backward at the current expansion rate, gives you the age of the universe. Measuring the expansion rate requires two pieces of information. First, you need to know how far away various galaxies are. Second, you need to know how fast they're moving away. Both measurements are challenging, but possible with modern telescopes. Distance gets measured using standard candles, objects with known true brightness. A particular type of supernova called type Ia always releases roughly the same amount of energy when it explodes. If you spot one of these supernovae in a distant galaxy, you can calculate the galaxy's distance by comparing the explosion's apparent brightness to its known true brightness. Velocity gets measured through redshift. Light from receding galaxies gets stretched to longer wavelengths, shifting toward the red end of the spectrum. The amount of shift reveals how fast the galaxy is moving away. It's the same principle as the Doppler effect you hear when an ambulance siren changes pitch as it passes by. Combine distance and velocity for many galaxies, plot them on a graph, and you get a line. The slope of that line is the Hubble constant, representing how fast the universe is expanding. Divide the speed of light by the Hubble constant and you get a time. That time is approximately how long the universe has been expanding. This method gives an age of about 13.8 billion years, remarkably close to the number from the cosmic microwave background. Two completely different approaches, based on different physics and different observations, reaching essentially the same conclusion. That agreement provides strong confidence that both methods are capturing something real about the universe. But there's a complication. Recent measurements of the Hubble constant don't quite agree with each other. Observations using the cosmic microwave background give one value. Observations using supernovae in nearby galaxies give a slightly higher value. The difference is only about 9%, but it's large enough to be concerning. This discrepancy, called the Hubble tension, has become one of the biggest puzzles in modern cosmology. It might indicate unknown physics affecting how the universe expands, or it might just mean someone's measurements contain subtle errors. Scientists are working furiously to figure out which. For now, though, both methods agree within their uncertainties. They both place the universe's age around 13.8 billion years, and that agreement is one of the strongest pieces of evidence supporting current cosmological models, which makes the Methuselah star's 16 billion year age even more problematic. Not one but two independent methods confirm the universe is younger than this star appears to be. Something has to give. Two witnesses telling the same story carries weight. When the cosmic microwave background method and the Hubble expansion method both produce ages around 13.8 billion years, that's not coincidence. These approaches use completely different physics. They rely on different observations. They make different assumptions, yet they reach strikingly similar conclusions. This agreement strengthens confidence enormously. If only one age measurement existed, scientists would worry about systematic errors unique to that method. Maybe the assumptions are wrong. Maybe the instruments have subtle biases. Maybe the physics isn't understood as well as believed. With only one measurement, those concerns can't be resolved. But when multiple independent methods agree, the chances of them all being wrong in the same way drop dramatically. It would require coordinated errors across different instruments, different physical models, and different types of observations. Possible, but increasingly unlikely. Think of it like triangulating your position using landmarks. If you take bearings from one mountain peak, you know you're somewhere along that line, but not exactly where. Add a second bearing from a different peak, and you narrow it down to a single point. The two measurements, working together, provide much more certainty than either alone. The cosmic microwave background approach looks backward in time to the early universe. It measures conditions when the universe was just 380,000 years old and uses physics to evolve those conditions forward to the present. Any errors in that physics or those measurements would affect the calculated age. The Hubble expansion approach looks at the present universe. It measures how fast galaxies are moving apart right now and runs that motion backward to find when everything was together. Any errors in distance measurements or expansion rates would affect this calculated age. These methods could fail independently. The microwave background analysis might have problems that don't affect expansion measurements. The expansion measurements might have issues that don't impact microwave background analysis. The fact that both produce similar ages despite their independence suggests both are capturing something true. That said, the methods aren't completely independent. They both assume general relativity correctly describes how gravity works on cosmic scales. If that assumption is wrong, both ages could be off in the same direction. A few alternative theories of gravity predict different cosmic expansion histories that would change the calculated age. But general relativity has been tested extensively. It correctly predicts the orbits of planets, the bending of light around massive objects, the existence of gravitational waves, and countless other phenomena. Abandoning it would require extraordinary evidence. An old star, however puzzling, doesn't meet that threshold. Scientists also have other, less precise ways to estimate the universe's age. They can measure the ages of the oldest star clusters and add time for those clusters to form after the Big Bang. They can study the abundance of radioactive elements created shortly after the universe began. These methods are less accurate, but provide additional consistency checks. All of them point toward the same general time frame, 13 to 14 billion years. The universe formed, structures grew, stars ignited, galaxies assembled, and eventually, humans evolved to figure all this out. Which brings us back to the central mystery. How could HD 140283 possibly be older than all of that? The answer required better measurements. And those measurements came from the most famous telescope ever built. The newest space telescope is finding impossible galaxies. When the James Webb Space Telescope launched in December 2021, astronomers expected amazing discoveries. This instrument can see farther into space and deeper into the past than anything before it. Its massive mirror collects infrared light that has been traveling since the early universe, revealing galaxies that formed when the cosmos was just a few 100 million years old. But nobody expected what Webb actually found. Those early galaxies are too big, too bright, and too well developed. According to current models of galaxy formation, they shouldn't exist yet. There simply hasn't been enough time for them to grow so large. One example is JWST 140, detected in 2024. This galaxy sits 33.6 billion light-years away. Because light takes time to travel, We see it as it appeared just 290 million years after the Big Bang. That's incredibly early. The universe was still in its cosmic infancy, yet this galaxy stretches about 1,600 light-years across. It shines with the combined light of hundreds of millions of stars. Those stars had to form, ignite, and evolve to their current state. Surrounding gas had to collapse into dense clouds, fragment into star-sized clumps, and begin nuclear fusion. All of that takes time. Current models suggest such a large, bright galaxy shouldn't have been possible so early. The universe was still relatively smooth and uniform back then. Gravity hadn't had enough time to pull matter into such dense, concentrated structures. Seeing this galaxy is like watching a 1-year-old baby run a marathon, completely unexpected based on normal development. And it's not alone. Webb has found dozens of these problematically early galaxies. Each one challenges our understanding of how quickly structures formed after the Big Bang. Some astronomers wonder if we're missing something fundamental about galaxy formation. Others suggest the universe might be older than currently calculated, giving more time for these galaxies to develop. This echoes the Methuselah star controversy from 2 decades earlier. Once again, observations are producing ages that don't fit the accepted cosmic timeline. Once again, scientists face a choice between questioning their measurements or questioning their understanding of the universe. A 2023 paper made headlines by proposing the universe is actually 26.7 billion years old, nearly twice the current estimate. The authors argued that modifying how we calculate cosmic expansion could resolve the Webb telescope observations and several other cosmological puzzles. If true, it would completely rewrite our understanding of cosmic history. But most astronomers remain skeptical. The 13.8 billion year age comes from multiple converging lines of evidence that would all need to be wrong in coordinated ways. That seems less likely than some hidden complexity in how early galaxies formed. Perhaps stars could form faster than models predict under the extreme conditions of the early universe. Perhaps dark matter clumped together more efficiently than expected. The debate continues. New observations keep challenging accepted ideas. But that's exactly how science should work. When reality contradicts theory, you don't ignore reality. You improve the theory or find better explanations. The universe doesn't care what we think should be possible. It simply does what it does. And sometimes, that means surprising us with stars and galaxies that seem far too old for comfort. A few scientists argue the universe is twice as old as textbooks claim. The standard age of 13.8 billion years rests on multiple pillars of evidence. But what if those pillars themselves stand on questionable foundations? What if the assumptions built into cosmological models contain fundamental errors that make everything appear younger than reality? Rajendra Gupta, a physicist at the University of Ottawa, published a controversial paper in 2023 proposing exactly that. He suggested modifying the equations that describe cosmic expansion. His altered models produced a universe age of 26.7 billion years, nearly double the accepted value. Gupta's theory attempts to solve several mysteries simultaneously. It explains why the James Webb Telescope found unexpectedly mature galaxies in the early universe. It resolves tensions in measurements of the expansion rate. And crucially for our story, it would make the original Methuselah star age calculation perfectly reasonable rather than impossible. But extraordinary claims need extraordinary evidence. Gupta's proposal requires changing fundamental physics that has been tested extensively. The equations he modifies have successfully predicted countless observations for decades. Altering them means explaining why they worked so well if they were actually wrong. Most cosmologists remain unconvinced. The evidence supporting the 13.8 billion year age comes from multiple independent sources that would all need to be reinterpreted. That's possible, but seems less likely than smaller corrections to specific measurements or models. Other alternative theories exist. Some propose that the speed of light has changed over cosmic time. which would affect age calculations that assume constant light speed. Others suggest gravity behaves differently on cosmic scales than Einstein's general relativity predicts. A few even question whether the Big Bang happened at all, proposing eternal or cyclical universes instead. Each theory has proponents who point to observations they claim support their ideas. The Methuselah star, the Webb telescope galaxies, the Hubble tension, unexplained cosmic structures. Every puzzle becomes potential evidence that mainstream cosmology has gone astray. But science doesn't work by collecting anomalies and declaring conventional wisdom wrong. You need a complete alternative framework that explains everything the old framework explained, plus the new observations it struggled with. So far, no alternative cosmology achieves that. Most explain one or two puzzles while creating bigger problems elsewhere. The steady-state theory, popular in the 1950s, proposed the universe has always existed without a beginning. It explained cosmic expansion by suggesting new matter continuously appears to fill the gaps as galaxies move apart, but it couldn't explain the cosmic microwave background radiation or the abundances of light elements. When those observations came along, the theory collapsed. Modern alternatives face similar challenges. They might resolve specific tensions, but fail to match the broad success of standard cosmology. The Big Bang framework correctly predicts the microwave background properties, light element ratios, galaxy distributions, and cosmic expansion history. Any replacement needs to match all of that while fixing the problems. That's an incredibly high bar, which is why most astronomers bet on smaller corrections rather than revolutionary new physics. Maybe the Hubble constant measurements need refinement. Maybe early galaxy formation was more efficient than models suggest. Maybe stellar age calculations for metal-poor stars contain subtle errors. Speaking of which, that last possibility was exactly what scientists investigating the Methuselah star decided to examine more carefully, and what they found would finally start unraveling the mystery. Calculating a star's birthday is nothing like dating rocks or trees. Geologists have it easy. They can examine rock samples in laboratories. They can measure radioactive decay products that accumulate predictably over time. They can use multiple isotopes to cross-check results. If one method gives a suspicious number, they can try 3 others to verify. Astronomers enjoy no such luxury. You cannot bring a star into a laboratory. You cannot touch it, sample it, or examine it up close. All you have is light. Photons that left the star's surface years or centuries ago and finally arrived at your telescope. From those photons alone, you must reconstruct billions of years of history. The process starts with basic measurements. How bright does the star appear from Earth? What's its color? What elements show up in its spectrum? How far away is it? Each measurement carries uncertainty. Distance measurements especially cause problems because small errors get amplified through later calculations. Once you have observational data, you turn to stellar evolution models. These computer simulations track how stars change over time based on fundamental physics. They calculate how nuclear fusion converts hydrogen to helium. They predict how energy flows from core to surface. They determine how stars expand or contract as they age. The models work well for average stars with plenty of heavy elements. Scientists have tested them against thousands of stars whose ages can be estimated through other methods, like their membership in star clusters of known age. The models accurately predict those stars' properties, but HD 140283 isn't average. Its extremely low metallicity puts it at the edge of parameter space where the models have been tested. Small changes in how the code handles metal-poor stars can shift calculated ages by billions of years. The uncertainty grows larger. Temperature estimates also matter enormously. A star's surface temperature affects how efficiently it radiates energy, which affects how fast it burns through fuel, which affects its age. But measuring temperature from spectra involves assumptions about the star's atmosphere. Different assumptions yield different temperatures and different ages. Chemical composition adds another layer of complexity. The ratio of helium to hydrogen affects stellar structure. Even tiny amounts of elements like carbon and oxygen influence the fusion process. If you miscalculate the composition slightly, the age calculation shifts significantly. Then there's the distance problem. If a star appears dimmer than expected, is that because it's farther away or because it's truly less luminous? Less luminous might mean older, having exhausted more fuel. Farther away means your brightness calculation was wrong and the age estimate needs revision. All these uncertainties compound. An error in distance affects luminosity, which affects temperature estimates, which affects evolutionary models, which affects calculated age. By the time you finish the calculation chain, small initial errors have grown into billion-year mistakes. This is why the 16 billion-year age for HD 140283 didn't immediately convince everyone the universe's age was wrong. Too many steps could contain hidden problems. The smart move was to improve the measurements and see if the age came down. But that required the most powerful telescope humanity had ever built, orbiting above Earth's distorting atmosphere, where it could see clearly across hundreds of light years. The answer orbited 200 miles above Earth's surface. The Hubble Space Telescope launched in April 1990 aboard the Space Shuttle Discovery. Its primary mirror stretched 7.9 feet across, smaller than many ground-based telescopes, but its location beyond Earth's atmosphere gave it unprecedented clarity. No air turbulence to blur images, no clouds to block observations, just pure, steady starlight captured with remarkable precision. After initial problems with mirror defects got fixed during a dramatic repair mission, Hubble became the most productive scientific instrument in history. It photographed distant galaxies, measured cosmic expansion, discovered dark energy, and revolutionized nearly every field of astronomy. And between 2003 and 2011, it turned its attention to HD 140283. The telescope observed the Methuselah star almost a dozen times using different instruments and techniques. Each observation added data that would help resolve the age controversy. The most important measurements involve parallax, the apparent shift in the star's position as Earth orbits around our stellar neighbor. Ground-based parallax measurements had worked well enough for the initial age calculation, but Earth's atmosphere constantly distorts incoming light, blurring stellar positions slightly. Even the best ground telescopes faced this limitation. Hubble suffered no such problems. Its parallax measurements achieved extraordinary precision. By tracking HD 140283's tiny apparent motion against more distant background stars, Hubble determined its distance to within about 2% uncertainty. That might not sound impressive, but it represented a major improvement over previous estimates. The new distance was slightly different from what earlier studies had used. Close, but not identical. And that small difference mattered enormously for age calculations. Remember, if you get distance wrong, you miscalculate true brightness. Wrong brightness leads to wrong temperature estimates, wrong evolutionary phase identification, and ultimately, wrong age. Hubble also gathered high-quality spectroscopic data. This revealed HD 140283's chemical composition in greater detail than ever before. Scientists could measure not just iron abundance, but also ratios of other heavy elements. These ratios provided clues about what kinds of supernovae had enriched the gas cloud that formed this star. The improved composition data allowed researchers to refine their stellar evolution models. They could adjust parameters to better match metal-poor stars specifically. Previous models had been optimized for stars with higher metallicity. Now the calculations could account more accurately for how extremely low metal content affects stellar structure and evolution. Additionally, Hubble measured the star's temperature and luminosity with better precision than ground-based observations could achieve. These parameters directly feed into age calculations. More accurate numbers going into the models meant more reliable ages coming out. A team led by Howard Bond from Pennsylvania State University analyzed all this new Hubble data carefully. They ran the numbers through updated stellar evolution models. They checked their work multiple times. Then they published their results in 2013. The new age came out lower than 16 billion years, much lower in fact. But as everyone waited anxiously to see if the cosmic crisis had been resolved, the number still carried unwelcome news. 14.46 billion years, still older than the universe, still impossible, but getting closer to possible. 14.46 billion years was progress, sort of. The Penn State team's announcement in 2013 represented a significant improvement over the original 16 billion year estimate. They'd shaved off about 1.5 billion years through better measurements and refined models. That wasn't nothing. It meant the earlier calculation had indeed contained errors that more precise data could correct, but it wasn't enough. The universe's age remained firmly at 13.8 billion years. The Methuselah star still appeared roughly 700 million years too old, still impossible, still breaking the fundamental rule that nothing can predate existence itself. The scientific community greeted the news with mixed feelings. On one hand, the age had moved in the right direction. That suggested the problem lay with stellar age calculations rather than cosmic age measurements. If better data reduced the star's age, perhaps even better data would reduce it further. On the other hand, 700 million years represents a huge gap. That's enough time for entire galaxies to form, for generations of massive stars to live and die, for cosmic structures to evolve dramatically. Having a star that old before the Big Bang was still deeply problematic. The Penn State team knew their result wasn't a complete solution. They carefully emphasized the uncertainty in their calculation. Every measurement and model parameter carried some error. When you combine all those errors properly, you get a range of possible ages rather than a single definite number. And that range turned out to be crucial. The team calculated an uncertainty of plus or minus 800 million years. In scientific notation, the star's age was 14.46 billion years, with an error margin of 0.8 billion years. That means the true age could be as high as 15.26 billion years or as low as 13.66 billion years. Read that last number again, 13.66 billion years. That falls comfortably below the universe's age of 13.8 billion years. If HD 140283's true age happened to lie at the lower end of the possible range, there was no crisis, no impossibility, no cosmic paradox. Of course, if the age fell at the upper end of the range, the problem remained. 15 billion years was still way too old, but at least now scientists had a plausible path to resolution. Improve the measurements further, reduce the uncertainty, and the age might drop below the cosmic threshold. This represented a major shift in perspective. Before the Penn State study, the Methuselah star appeared to be a fundamental challenge to cosmology. After the study, it looked more like a measurement problem that additional observations could solve. The tension had lessened dramatically, even though it hadn't disappeared entirely. Media coverage reflected this change. Instead of headlines screaming about physics being broken, articles now discussed how scientists were closing in on the mystery. The tone shifted from panic to cautious optimism. Maybe the universe wasn't wrong after all. Maybe we just needed better telescopes. But science demands certainty, not maybes. An age estimate that spans both sides of the cosmic threshold isn't good enough. Researchers needed to pin down that number more precisely, and that's exactly what they set out to do over the next several years, with increasingly sophisticated observations and models. The 800 million year uncertainty changed everything. Before the Penn State study, most people treated the 16 billion year age as a hard number. The star was 16 billion years old, period. That made it impossible, paradoxical, physics breaking. But treating any scientific measurement as absolutely certain misunderstands how science actually works. Every measurement has uncertainty. When you measure your height, the result depends on whether you use a ruler marked in inches or millimeters, whether you stand perfectly straight, whether you measure in the morning or evening after your spine has compressed slightly. Real measurements always come with some wiggle room. For stellar ages, that wiggle room gets large. Remember all those compounding uncertainties from earlier? Distance measurements carry a few percent error. Temperature estimates have their own uncertainty range. Chemical composition measurements aren't perfect. Stellar evolution models contain assumptions that might not be exactly right. When you propagate all these uncertainties through the age calculation, they multiply. A 2% distance error might translate to a 5% age error. Add in temperature and composition uncertainties, and suddenly, you're looking at error bars spanning billions of years. The 0.8 billion year uncertainty in the Penn State result reflected this reality. The team carefully tracked every source of error and combined them properly to produce that range. It was honest science, acknowledging the limits of what their data could conclusively prove, and those limits mattered enormously. An age of 14.46 plus or minus 0.8 meant the measurement was consistent with ages anywhere from 13.66 to 15.26 billion years. The lower bound fell below the universe's age. Therefore, the measurement didn't actually prove the star was older than the universe. This might sound like a technicality, but it's fundamental to understanding scientific claims. When uncertainties are large enough that multiple explanations fit the data, you cannot draw definitive conclusions. You can say the data suggests certain possibilities or makes others unlikely, but you cannot claim proof. Imagine a murder trial where the time of death is estimated at midnight plus or minus 3 hours. That means death could have occurred anywhere between 9 p.m. and 3 a.m. If the suspect has an alibi for 9 p.m. to 11 p.m., they're not necessarily innocent because death might have happened later. But if they have an alibi for the entire window, they're clearly innocent. The Methuselah star was like that. Before the Penn State study, the estimated time of birth fell entirely before the universe began. Clear impossibility. After the study, the birth time window straddled the Big Bang. Possible, but not definite impossibility. That shifted the burden of proof. Instead of cosmologists needing to explain how a star could be older than the universe, stellar astronomers needed to narrow down the age estimate to figure out whether it actually was impossible or just appeared that way due to measurement limitations. The path forward was clear. Get better data, reduce the uncertainties, pin down that age with enough precision to definitively say whether it fell before or after the Big Bang. Multiple research teams accepted that challenge, and over the next several years, they made remarkable progress using increasingly refined techniques. Science works by gradually approaching truth through repeated refinement. The Penn State study in 2013 wasn't the end of efforts to measure HD 140283's age. It was just one step in an ongoing process. Other research teams continued improving measurements and models, each pushing toward greater precision. A 2014 study nudged the age down to 14.27 billion years. The change seemed small, less than 200 million years, but it represented continued progress in the right direction. Better distance measurements contributed. Improved stellar atmosphere models helped. More sophisticated handling of chemical composition data made a difference. Each study built on previous work while adding new insights. One team might focus on refining temperature estimates using advanced spectroscopic techniques. Another might improve the stellar evolution code to better handle metal-poor stars. A third might gather additional parallax measurements to nail down distance more precisely. The uncertainties gradually shrank too. That 2014 study reported errors around plus or minus 700 million years, down from 800 million in the Penn State work. The age estimate was getting more precise, even as it was getting lower. Both trends were encouraging. Other researchers took different approaches. Instead of just measuring HD 140283, they studied similar metal-poor stars to calibrate their models. If you can measure ages for multiple ancient stars, and they all give consistent results, that builds confidence. If they scatter wildly, something's wrong with your methods. The comparisons generally supported the revised ages. Other extremely old stars didn't appear older than the universe either. Their ages clustered around 12 to 13 billion years, comfortably below the cosmic limit. This suggested the techniques were working properly, and HD 140283's age would continue dropping as measurements improved. Throughout this period, new telescopes and instruments came online. The Gaia spacecraft, launched by the European Space Agency in 2013, began making even more precise parallax measurements than Hubble. For stars like HD 140283, Gaia could determine distances to within 1% or better. That dramatically reduced one major source of uncertainty. Better spectroscopic instruments on ground-based telescopes contributed too. Advances in detector technology and adaptive optics systems that compensate for atmospheric distortion let astronomers gather higher quality spectra. More detailed spectra meant better composition measurements and temperature estimates. The stellar evolution models themselves improved. As computers got faster, researchers could run more sophisticated simulations that included previously neglected physics. Things like turbulence in stellar atmospheres, rotation effects, and subtle nuclear reactions all got incorporated more accurately. By 2020, the picture had clarified considerably. Multiple independent studies using different methods all converged on ages for HD 140283 between 12 and 13 billion years. The star was definitely ancient, probably one of the oldest in our galaxy. But it wasn't impossibly ancient anymore. The final major revision came in 2021. A comprehensive study incorporating all available data and the latest models produced the most reliable age estimate yet. The number they calculated resolved the decade-long controversy once and for all. And just like that, the star that had threatened to overturn cosmology became simply a remarkable example of how science corrects itself. 12 billion years. Finally, a number that made sense. The 2021 study represented the culmination of decades of increasingly precise measurements. Researchers had access to the best distance measurements from Gaia. They used the highest quality spectroscopic data from multiple telescopes. They employed the most sophisticated stellar evolution models ever developed. Everything came together. When they ran the calculations, HD 140283's age came out to approximately 12 billion years, give or take about half a billion years. Even at the upper end of uncertainty, 12.5 billion years, the star remained comfortably younger than the universe's 13.8 billion years. The paradox had dissolved. The difference between 12 and 16 billion years might seem like someone just kept making arithmetic mistakes. But that misses the point. Those 4 billion years of correction came from genuine improvements in understanding. Early measurements were done with the best available tools and methods. As tools and methods improved, the estimates naturally got better. This is exactly how science is supposed to work. Initial measurements are rough approximations. You know they contain errors, but you don't know how large those errors are. So you publish the results tentatively, make clear the limitations, and invite others to improve upon them. Over time, the measurements converge toward truth. The key insight was recognizing that calculating stellar ages involves a long chain of measurements and models. Each link in that chain carried uncertainty. Early studies used the best estimates available for distance, temperature, luminosity, and composition. But those estimates all had significant error bars. As measurements improved, each parameter got refined. Distance changed from 190 light-years with 5% uncertainty to 190 light-years with 1% uncertainty. That tighter precision affected everything downstream. Temperature estimates improved. Luminosity calculations became more accurate. The models could be tuned more precisely. Additionally, the stellar evolution codes themselves got better. Early versions made simplifying assumptions about how metal-poor stars behave. Later versions included more detailed physics. They accounted for things like diffusion of elements through the stellar interior, rotation effects on structure, and magnetic field impacts on energy transport. None of these improvements individually made a massive difference, but combined, They pushed the calculated age steadily downward from 16 billion to 14 billion to 12 billion years. Each step was small. The cumulative effect was transformative. The 2021 study also highlighted something important about scientific uncertainty. The original 16 billion year estimate wasn't wrong in the sense of being careless or fraudulent. It was wrong in the sense of being based on incomplete data and imperfect models. The researchers who calculated it did everything correctly, given what they knew at the time. Science doesn't demand perfection immediately. It demands honesty about limitations and openness to revision. The teams that measured HD 140283's age embodied those principles. They reported their results transparently, acknowledged uncertainties clearly, and welcomed efforts to improve the measurements. The final age of 12 billion years solved the cosmic crisis. No longer did the star threaten fundamental cosmology. No longer did skeptics have ammunition to attack the Big Bang. The universe's age remained secure at 13.8 billion years. But the story doesn't end there, because HD 140283, despite no longer being impossible, remained scientifically fascinating for entirely different reasons. The Methuselah star changed astronomy before anyone knew it was special. Back in 1951, when Joseph Chamberlain first analyzed HD 140283's spectrum, he discovered something revolutionary. This was the first star ever found with dramatically lower heavy element content than our stellar neighbor. That single observation opened up an entirely new way of understanding cosmic history. Before that discovery, astronomers assumed all stars had roughly similar compositions. They knew different stars had different temperatures and sizes, but they thought the mix of elements stayed relatively constant. Chamberlain's finding proved that assumption wrong. Stars could have wildly different chemical makeups depending on when they formed. This realization led directly to the population classification system still used today. If stars varied in metal content, that variation must mean something. It must encode information about the conditions present when each star formed. Low metal content meant formation in the early universe when few supernovae had occurred. High metal content meant later formation from enriched material. That insight was foundational. It gave astronomers a tool to probe cosmic history without needing time machines. Just measure a star's composition, and you immediately know roughly when it formed relative to other stars. Simple, yet powerful. HD 140283 served as the prototype for this entire field of study. After Chamberlain's paper, other astronomers began searching for similar metal-poor stars. They found them scattered throughout our galaxy, particularly in the halo, a roughly spherical region surrounding the Milky Way's disk. These halo stars represent some of the oldest objects in our galaxy. By studying populations of metal-poor stars, scientists reconstructed how the Milky Way formed and evolved. The halo stars formed first, before the galaxy had settled into its current disk shape. Later generations formed within the disk from progressively more enriched gas. The story was written in stellar chemistry. This work also connected to another major astronomical revolution happening simultaneously. In the 1940s and 50s, scientists were figuring out how stars generate energy through nuclear fusion. They realized fusion could create heavier elements from lighter ones. But where did those heavier elements actually come from? The answer came from studying stellar evolution and supernovae. Massive stars could fuse elements up to iron in their cores. When they exploded, they created elements heavier than iron and scattered everything into space. The next generation of stars formed from that enriched material, and the cycle repeated. HD 140283's low metallicity confirmed this picture. Here was a star that formed when very few supernovae had occurred. It contained just traces of heavy elements, exactly as the theory predicted. Without this observational confirmation, the entire framework of nucleosynthesis might have remained speculative much longer. Beyond its scientific importance, the Methuselah star taught a broader lesson about how science handles anomalies. When observations clash with theory, you don't immediately throw out the theory. You check the observations carefully. You look for errors or uncertainties. You refine your measurements. Usually, the contradiction resolves. But sometimes it doesn't. Sometimes the observations are correct and theory really is wrong. Good scientists remain open to both possibilities, while carefully evaluating which is more likely based on all available evidence. In this case, better observations resolved the contradiction. But the process demonstrated science working exactly as it should. HD 140283 is currently just entering old age. Despite being 12 billion years old, this ancient star has barely lived at all in cosmic terms. It currently exists as a subgiant, having exhausted the hydrogen in its core and begun fusing hydrogen in a shell around that core. This phase started relatively recently on cosmic timescales, perhaps within the last few 100 million years. Our stellar neighbor will reach the subgiant phase in about 5 billion years. It will expand slightly, becoming more luminous as it adjusts to the new energy source. This phase lasts roughly 1 billion years before the next transformation begins. HD 140283 entered this stage billions of years ago, but still has substantial time remaining. Eventually, the hydrogen shell will produce enough helium to accumulate around the core. The star will continue expanding dramatically, becoming a red giant. Its outer layers will extend outward, possibly growing to hundreds of times its current size. The surface will cool to reddish temperatures, while the total energy output increases enormously. During the red giant phase, the core will contract and heat until temperatures reach 100 million degrees. At that point, helium fusion ignites. 3 helium nuclei combine to form carbon in a reaction called the triple alpha process. This new energy source stabilizes the star temporarily, though it burns through helium fuel much faster than it previously burned hydrogen. After exhausting its helium supply, HD 140283 will lack the mass needed to ignite carbon fusion. More massive stars can continue fusing heavier elements, but this star falls below that threshold. Without a new energy source, the core becomes inert again. The outer layers, no longer supported by fusion energy, will begin drifting away. These expelled outer layers form what astronomers call a planetary nebula, though it has nothing to do with planets. The name comes from early observers who thought these objects looked like planetary disks through small telescopes. In reality, they're expanding shells of gas glowing from the ultraviolet light of the exposed stellar core. That core becomes a white dwarf, an incredibly dense object about the size of Earth but containing roughly half the star's original mass. A teaspoon of white dwarf material would weigh several tons on Earth. The density comes from electrons being packed together as tightly as quantum physics allows. White dwarfs don't fuse atoms. They're not generating new energy. They simply radiate away the tremendous heat left over from their stellar lifetime. This process takes an incredibly long time because white dwarfs have small surface areas and cool slowly. Current calculations suggest a white dwarf will take about 10 trillion years to cool completely. 10 trillion years is longer than the current age of the universe, by a factor of about 700. When HD 140283 eventually becomes a black dwarf, a completely cooled white dwarf that no longer glows, the universe will be unimaginably old. Most stars will have died. Galaxies will have dispersed. The cosmos will be a cold, dark place with only scattered remnants of its former glory. But all of that lies far in the future. Right now, HD 140283 continues burning steadily in Libra, fusing hydrogen into helium, shining with the light of a subgiant star. It has existed for 12 billion years. It will continue existing, in one form or another, for trillions more. And right now, tonight, you can see it. You don't need a massive telescope to see one of the universe's oldest stars. HD 140283 sits in the constellation Libra, visible from most locations on Earth during certain times of year. Its coordinates are well documented. Any star chart or astronomy app can guide you right to it. The challenge isn't finding where to point. The challenge is seeing something with apparent magnitude 7. Human eyes can see down to magnitude 6 under perfectly dark skies. Magnitude 7 falls just below that threshold. You might glimpse it on an exceptional night far from light pollution, but probably not reliably. Fortunately, even basic binoculars solve this problem. 7 times 50 binoculars easily reveal magnitude 7 stars. 10 times 50 binoculars make them obvious. Small telescopes make it trivial. Any telescope 4 inches or larger will show HD 140283 clearly as a distinct point of light. It won't look particularly impressive. Stars generally don't through telescopes because they're too far away to show disks. Even the closest stars appear as dimensionless points. But that point is special. The best time to observe depends on your latitude. From northern temperate latitudes, Libra is best seen in spring and early summer when it reaches higher in the sky after sunset. From southern latitudes, it remains visible longer into the year. Check a star chart for your specific location and date. You'll need dark skies. Light pollution washes out faint objects, making magnitude 7 stars invisible even through binoculars. Drive away from cities if possible. Let your eyes adapt to darkness for at least 20 minutes before observing. Avoid looking at white lights, including phone screens, unless you use red night mode. Finding the exact star requires some patience. Libra doesn't contain many bright stars, so the constellation can be tricky to identify initially. Use a bright planet or the brighter stars of nearby Virgo and Scorpius as reference points. Once you locate Libra, star charts will guide you to HD 140283's specific position. When you finally spot it, take a moment to appreciate what you're seeing. That light left the star's surface about 190 years ago, around 1835. It traveled through space at 186,000 miles per second, covering nearly 2 trillion miles to reach your eye. More remarkably, that light comes from a star that witnessed the early days of our galaxy. HD 140283 was already ancient when Earth formed 4.6 billion years ago. It existed before the dinosaurs, before complex life, before our planet even existed. The atoms in your body are younger than this star's light. This is what makes astronomy uniquely accessible compared to other sciences. A particle physicist needs billion-dollar colliders to study their subject. A molecular biologist needs sophisticated laboratory equipment. But an astronomer just needs clear skies and basic optical equipment to observe objects more ancient than imagination. HD 140283 isn't the farthest thing you can see with binoculars, or the brightest, or the strangest, but it might be the oldest. And there's something profound about pointing your eyes or binoculars at a particular direction and collecting photons from a star that formed 12 billion years ago, capturing light that bridges most of cosmic history. Look up, find it, and remember you're seeing one of the oldest objects still visible to human observation, the Methuselah star, ancient beyond comprehension, yet close enough to glimpse from your backyard. HD 140283 might not hold the record for long. Astronomers are actively hunting for even more ancient stars scattered throughout our galaxy. Every metal-poor star discovered adds another data point to our understanding of the early universe. Some of these stars might approach the maximum possible age, formed within the first few 100 million years after the Big Bang. One candidate, discovered in 2014, created immediate excitement. SMSS J031300.36 to 670839.3, located in the halo of the Milky Way, showed iron content so low that scientists initially couldn't detect any at all. Later measurements found traces, but at levels 100,000 times lower than our stellar neighbor. This star formed from gas enriched by perhaps a single supernova. Its calculated age came out around 13.5 billion years, roughly 1.5 billion years younger than the universe, not quite as old as the original HD 140283 estimate. but still incredibly ancient. This star witnessed the universe when it was barely 200 million years old, when the first galaxies were just beginning to assemble. Another fascinating discovery came from studying ultra-faint dwarf galaxies, tiny collections of stars orbiting the Milky Way. These small galaxies contain some of the oldest known stars, many with ages approaching 13 billion years. They represent fossil remnants of galaxy formation, preserved in cosmic amber. One star in these dwarf galaxies, catalogued as 2-mass Jonate 082002-51043778b, shows similar metal poverty to HD 140283. Its age calculations hover around 13.4 billion years. Finding multiple stars at these extreme ages confirms the dating methods work consistently. If errors were throwing ages off randomly, you wouldn't see this clustering near the cosmic limit, but astronomers want to push further. They're searching for stars that might have formed from gas enriched by population 3 supernovae. These would be the direct descendants of the first stellar generation, containing the chemical fingerprints of those primordial giants. Finding such a star would be like discovering a dinosaur fossil that still has soft tissue attached. The challenge is that truly ancient stars are incredibly rare. Most formed long ago in the early universe, but the vast majority have already died. Stars massive enough to be bright and easy to detect burned out billions of years ago. The ones remaining are small, faint, and scattered randomly through the galaxy's halo. Modern surveys are making progress, though. Projects like the Pristine Survey and the Hamburg ESO survey systematically search for metal-poor candidates. They examine millions of stars, measuring spectra to identify those with unusually low heavy element content. The promising candidates then get detailed follow-up observations. Each discovery helps map when star formation began in different regions of the early universe. Did all parts of the universe start forming stars simultaneously, or did some regions begin earlier? Did the Milky Way form stars before or after other nearby galaxies? These questions require finding and dating as many ancient stars as possible. HD 140283 pioneered this field back in 1951. Now, 70 years later, astronomers are finding its cosmic siblings and cousins. Each one adds detail to the story of our galaxy's birth. And somewhere out there, an even older star might be waiting for discovery, pushing even closer to the moment when starlight first illuminated the darkness. Ancient stars remember when galaxies were being born. HD 140283 formed during a crucial period in cosmic history. The universe was transitioning from a simple collection of scattered stars to a complex web of organized galaxies. Understanding exactly when stars like this ignited helps astronomers reconstruct that transformation. Current evidence suggests the first small protogalaxies appeared around 200 to 400 million years after the Big Bang. These weren't majestic spiral or elliptical galaxies like we see today. They were tiny, chaotic collections of gas and stars, maybe a few hundred light years across, containing only millions of stars rather than billions. These baby galaxies were incredibly violent places. Star formation occurred at frantic rates. Supernovae exploded constantly, blasting metal-enriched gas into surrounding space. Black holes grew rapidly in galaxy centers, consuming matter and releasing tremendous energy. The early universe was far more active and chaotic than the relatively calm cosmos we observe today. HD 140283 probably formed either in one of these early protogalaxies or in the halo region as they began merging together. Its low metallicity indicates formation before much enrichment had occurred. The star witnessed the Milky Way's assembly from scattered building blocks into a coherent structure. This matters because galaxy formation remains one of cosmology's biggest unsolved puzzles. Computer simulations can show gas collapsing under gravity and stars igniting, but the details depend on dozens of parameters that aren't perfectly known. Things like how efficiently gas cools, how star formation responds to feedback from supernovae, and how dark matter influences the process. By studying stars like HD 140283, astronomers can test these simulations against reality. If models predict certain metal enrichment levels at specific times and observations match those predictions, that builds confidence. If observations disagree, the models need adjustment. The age of HD 140283 tells us that substantial star formation was already happening 12 billion years ago. The universe was less than 2 billion years old at that point. Gas had collapsed into structures, fragmented into star-forming clouds, and ignited nuclear fusion. The cosmic infrastructure for making stars was already well established. This matches what the James Webb Telescope is finding. Those surprisingly large galaxies at high redshifts aren't quite as shocking when we consider that stars like HD 140283 prove efficient star formation happened early. The universe didn't waste time. As soon as conditions allowed, gas began forming stars at impressive rates. But questions remain. Why did some regions form stars earlier than others? What determined whether a gas cloud would form one massive star or many small ones? How did the first heavy elements disperse through space to enrich surrounding material? Every ancient star studied provides clues. HD 140283's motion through the galaxy also tells a story. It orbits in an elongated path typical of halo stars, occasionally plunging through the galactic disk before swinging back out. This orbit preserved it from the violent processes occurring in the disk, where supernovae and stellar collisions are more common. That's probably why it survived 12 billion years intact. The star is a time capsule, preserving information about conditions billions of years ago. Its composition reveals what the early galaxy was like. Its motion traces ancient dynamical processes. Its mere existence confirms that low-mass stars formed alongside massive ones in the first stellar generations. HD 140283 wasn't the only timing puzzle challenging astronomers. The universe contains numerous objects whose ages initially seemed impossible or contradictory. Each one forced scientists to carefully examine their assumptions and improve their methods. The resolution of these mysteries often revealed new insights about cosmic history. Globular clusters presented a similar challenge to the Methuselah star. These dense spherical collections of hundreds of thousands of stars orbit in the halos of galaxies. Early age estimates for the oldest globular clusters came out around 16 to 18 billion years. Clearly impossible if the universe was only 13.8 billion years old. Just like with HD 140283, better measurements resolved the contradiction. Improved distance estimates from the Hipparcos and Gaia satellites changed the calculated ages. Refined stellar evolution models that better handled low metallicity stars made a difference. By the 2010s, globular cluster ages had dropped to around 12 to 13 billion years, comfortably younger than the universe. The oldest white dwarfs created another timing issue. These stellar remnants cool predictably over billions of years, making them cosmic clocks. By measuring how cool the oldest white dwarfs have become, astronomers can estimate how long they've been cooling. Early calculations suggested some were older than the universe. Again, better measurements fixed the problem. Improved understanding of white dwarf cooling physics, better distance measurements, and refined atmospheric models all contributed. The oldest confirmed white dwarfs now show ages around 12 to 13 billion years, consistent with other ancient objects. A different kind of age puzzle involves the expansion rate of the universe. Two methods for measuring the Hubble constant give slightly different values. One uses the cosmic microwave background, looking at the early universe. The other uses supernovae and other distance indicators, looking at the nearby universe. The discrepancy is only about 9%, but it's persistent and statistically significant. This Hubble tension, as astronomers call it, might indicate unknown physics affecting cosmic expansion, or it might reflect subtle measurement errors in one or both methods. Resolving it will either reveal new phenomena or teach us about systematic biases in our observations. Either way, the answer will be scientifically valuable. Fast radio bursts present yet another mystery. These millisecond pulses of radio waves come from distant galaxies. Some show patterns suggesting they come from incredibly dense objects like neutron stars. But calculating when and how these objects formed requires understanding the host galaxy's history. The ages don't always match expectations, suggesting gaps in our models. The most distant quasars offer similar puzzles. These brilliant objects, powered by supermassive black holes, appear at times when the universe was less than 1 billion years old, but forming billion stellar mass black holes so quickly challenges current theories. Either black holes grow faster than models predict, or they started from more massive seeds than expected, or something else is going on. Each of these mysteries follows a similar pattern to the Methuselah star saga. Initial observations suggest something impossible. Scientists carefully check measurements and models. Usually, improved data resolves the contradiction. Occasionally, it reveals genuinely new physics. The process of resolving these puzzles drives astronomy forward, forcing constant refinement of our understanding. The quest to measure cosmic ages with perfect precision continues. New telescopes and instruments coming online over the next decade will revolutionize how astronomers measure stellar ages. The precision that took decades to achieve for HD 140283 will soon become routine for thousands of stars. This explosion of data will transform our understanding of galactic history. The extremely large telescope, currently under construction in Chile, will have a primary mirror 108 feet across when completed. That's nearly 5 times larger than any existing optical telescope. Its light-gathering power and resolving ability will enable detailed spectroscopy of faint ancient stars that current instruments barely detect. This matters because many potential ancient stars remain too faint for detailed study right now. Astronomers can identify candidates through rough measurements, but calculating precise ages requires high-quality spectra that only massive telescopes can provide. The extremely large telescope will turn those candidates into precisely dated cosmic fossils. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will survey huge portions of the sky simultaneously. Unlike Hubble, which studies small fields in detail, Roman will observe wide areas quickly. This combination of survey speed and space-based precision will identify thousands of ancient star candidates for follow-up observations. Improved stellar evolution codes will continue enhancing age calculations. As computers grow more powerful, simulations can include increasingly complex physics. Things like turbulent mixing in stellar interiors, magnetic field effects on structure, and detailed nuclear reaction networks all improve model accuracy. Each refinement reduces uncertainty in calculated ages. Machine learning is already starting to contribute. Algorithms can analyze stellar spectra faster and more consistently than humans. They can identify subtle patterns that indicate age, metallicity, and other properties. As training datasets improve, these tools will become increasingly valuable for processing the enormous quantities of data future surveys will generate. Gravitational wave astronomy might eventually contribute to cosmic age measurements in unexpected ways. When neutron stars or black holes merge, they produce gravitational waves we can detect. If we could determine when these compact objects formed based on their mergers, that would provide independent age estimates for different stellar populations. Improvements in distance measurements will continue reducing age uncertainties. The Gaia satellite is already in its extended mission, measuring parallaxes for over 1 billion stars with unprecedented precision. Its full dataset, when completely processed, will revolutionize our 3-dimensional map of the galaxy and enable more accurate age determinations for countless stars. Theoretical advances matter too. Better understanding of Big Bang nucleosynthesis, improved models of the first stars, and refined calculations of cosmic expansion history all feed into age determinations. Sometimes the breakthroughs come from observations, but just as often they come from theorists finding better ways to interpret existing data. The goal isn't just satisfying curiosity. Precise cosmic ages help constrain fundamental physics. They test theories of gravity, dark matter, and dark energy. They reveal how structure formed in the early universe. They constrain the properties of mysterious components making up most of cosmic energy. HD 140283 pioneered this journey 70 years ago, when Joseph Chamberlain first noticed its unusual composition. Now, as technology advances and understanding deepens, that ancient star's cosmic siblings will tell us even more about where we came from and how our universe evolved from simplicity to the magnificent complexity surrounding us today.